Welcome to the second week of open course on diffusion in multi-component solids. This is the 6th lecture in the series, and in this lecture we will start with solution thermodynamics. I will first explain the concept of thermodynamic activity, and later we will derive the equation for Gibbs free energy of mixing in terms of activities of the components. Interdiffusion is a process of intermixing that drives many transformations, that is the transformation from non-stable state to a stable state. And so it is important for us for this class to understand the Gibbs free energy changes associated with the process of mixing. So next couple of classes we will talk about solution thermodynamics or the process of intermixing and Gibbs free energy changes associated with it. So when we talk about solutions, thermodynamic activity is an important parameter. As you all know, the diffusion is driven down the gradient of chemical potentials, or equivalently down the gradient of thermodynamic activities. So let us try to understand what is thermodynamic activity, what is the physical significance of thermodynamic activity parameter. Okay. So as you all know, any condensed phase, that is a solid or liquid, builds up an equilibrium vapor pressure above its surface, right. So consider, for example, a solid which is contained in a container. Let us say this solid is a pure element A, and let us say initially the chamber was evacuated. Now A has to exert an equilibrium vapor pressure, and since the chamber was evacuated, so this is a non-equilibrium state. So what happens, some of the A atoms will go into the vapor phase, right, that will build up the vapor pressure, and this process will continue until the pressure becomes equal to, this is at equilibrium at temperature T. So P0, or let us say PA0 to be precise, is the equilibrium vapor pressure of A at temperature T. So the evaporation will stop when the pressure inside the chamber reaches PA0. But on the atomistic scale, there is still the process of evaporation is going on, but it is counterbalanced by the process of reverse process of condensation. So what is happening at the atomistic level is there is a continuous evaporation of some atoms of A from solid into the vapor phase, but at the same time some atoms are hitting back on the solid surface and they are getting condensed. So at equilibrium the rate of condensation is equal to the rate of evaporation, and so we do not see any net evaporation or condensation when the equilibrium is established, right. So let us try to analyze how these rates are affected with the composition. So initially let us say the rate of evaporation is REA. So how the evaporation process occurs? Basically what we are doing is plucking out an A atom from the solid surface and putting it into the vapor phase. So now all of us know that in solid all the atoms are in their equilibrium positions, right, they are continuously vibrating about their equilibrium positions. So if we consider this atomic arrangement, essentially each atom is located at a what we call as potential energy well, right. So these are the equilibrium positions, which means at these positions or at the regular lattice sites the forces are balanced, there are interactions between the atoms, but at the equilibrium positions these interactions are balanced, right. So essentially those are the minimum energy positions. So those are the potential energy wells. If all the atoms are identical, right, or the depth of these potential energy wells are same, let us call it as EA. So, in order to remove one atom from the surface, right, there has to be some work done, right. So, the atom has to gain enough energy, it has to overcome this activation barrier EA, and obviously, so rate of evaporation will be proportional to exponential minus EA by KT, right. This is the Arrhenius equation. Now, what about the condensation? So, for condensation to occur, some of the A atom have to hit on the surface and become the part of A. So, we know in the vapor phase the A atoms are continuously undergoing the translational motion, and some of the A atoms will hit solid A and become part of A, that is the condensation process. So, essentially the rate of condensation RC of A will be proportional to vapor pressure, right. So, if it is pure A, it will be proportional to Pa 0, because pressure is essentially it quantifies how many atoms are hitting the wall per unit time, right. So, RCA we can write it as K times Pa 0, and we know at equilibrium essentially the rate of evaporation is same as rate of condensation, and so we can write REA is equal to K times Pa 0. Let us call this equation 1. Now, suppose instead of pure A, we initially had a solution of A and another component B, then what difference it will make? We know when A is inside solution instead of pure A. So, we need to consider the equilibrium partial vapor pressure, right, and obviously the vapor pressure Pa exerted by element A when it is inside the solution will be less than Pa 0, right. So, now how the rate of condensation and rate of evaporation will change? Now, for evaporation of A atom can occur only from the sides of A, right. So, we have to reduce the intrinsic rate of evaporation of A by the factor XA, that is the mole fraction of A, assuming that the concentration of the surface is same as the bulk concentration, right. So, we need to apply the factor XA to the intrinsic rate of evaporation, and now that will be on the other side rate of condensation will be proportional to Pa, because the new equilibrium partial vapor pressure is Pa, right. So, this is our equation 2. So, if we divide 2 by 1, what we get XA is equal to Pa over Pa 0, or Pa is equal to XA times Pa 0. Similarly, for B we can write Pb is equal to Xb times Pb 0, where Pb 0 is the equilibrium vapor pressure exerted by pure B at temperature T. So, all this we are considering at same temperature T, right. So, this basically is called Raoult's law. So, if we try to plot how the equilibrium partial pressure Pa varies with composition, let us say with Xa, y axis is the partial vapor pressure. So, for A, if the x axis is Xa, we have Xa equal to 0, obviously at Xa equal to 0 Pa is equal to 0, and when Xa equal to 1 our Pa will be Pa 0, and the Raoult's law tells me that there is a straight line, relation. Similarly, if we plot Pb as a function of Xb, Xb will be in the opposite direction. So, this axis is Xb equal to 1. So, Pb will be equal to Pb 0, and Xb equal to 0, Pb will be 0. So, when the solution follows Raoult's law, we say it is an ideal solution, right. So, now there is an assumption that we have made here, which we did not express earlier. What is that? See, when we wrote this equation 1 and 2, right, for pure element as well as for the solution, right, we are assuming REA is same, that is intrinsic rate of evaporation is not changing for A, whether it is a pure A or whether it is inside a solution, right. This can happen when either there are no interactions between A and B, or the interactions between A and B are same as between A and A or between B and B. So, the interactions are same. Okay. So, in this case we call it an ideal solution or Raoultian solution. So, basically ideal solutions are characterized by no interactions between the atoms or all the interactions are same. So, let us see how the situation changes when we have the interactions between AA and BB and AB which are different, right. So, what will happen in that case? So, suppose AB interactions are stronger than AA and BB. What will happen if we are considering a solution of A and B? What will happen to the potential well? Obviously, there will be some AB bonds, right, which are stronger than AA bonds, and so the A atom which is surrounded by B atom will lie at a deeper potential energy well, right. So, basically if we compare with this, in AB solution the potential energy well for A will be deeper. So, let us call this EA prime, which means that to pluck one atom of A out of the solution, more work will be required to be done as against pure A. So, obviously the intrinsic rate of evaporation will change, right. So, we can write this equation 2 for the solution case as XA times RE prime A is equal to K times PA, and we know that for this case when AB interactions are stronger than AA and BB, RE prime A will be less than RE of A. So, now if we divide equation 3 by 1, what we get? So, divide 3 by 1, RE prime A divided by REA times XA is equal to PA over PA0, or PA is equal to RE prime A by REA times XA times PA0. And since RE prime A is less than REA, PA is actually less than XA times PA0, right. So, basically if we plot the relation between PA and XA, it will lie below the Raoultian line. So, this will give me a what is called as negative deviation from ideality. PA is equal to PA0. So, if we try to plot the relation between PA and XA, obviously this is the Raoult law line, and since RE prime A is less than REA, there will be a negative deviation, right. So, it will be something like this. Now, when we are considering a dilute solution, when the solution of A and B is dilute, What does that mean? That means that most of the A atoms are surrounded only by B atoms. So, most of the bonds that A is involved in are AB type of bonds, right, which means Re prime is basically constant as a function of concentration as long as the concentration is very low, right. So, basically initially there will be a linear relation between Pa and Xa, right. So, this is called Henry's law. Now, what happens as we increase the concentration of A? With the increasing concentration of A, probability of forming AA bonds is more, right, and when there are AA bonds, since AA bonds are weaker than AB, right, the overall or it will raise the overall potential energy well, right. So, the potential energy well will be lesser and lesser deeper as Xa increases, which means then there will be deviation from the Henry's law line at higher concentrations. And what happens as Xa tends to 1, as Xa tends to 1, again all A atoms will be mostly surrounded by only A atoms. The intrinsic rate of evaporation will be similar to the intrinsic rate of evaporation of pure A, and so as Xa tends to 1, this will follow the Rawls law line, right. So, this is basically for negative deviation from ideality. Now, what happens if Re prime A is greater than Re of A, which means AB bonds are weaker than AA and BB bonds. With the similar logic we can show that in that case there will be a positive deviation, right. So, this will be for this is if Re prime A is greater than ReA, that is when AB bonds are weaker than AA and BB bonds. Okay. So, now can define the quantity Pa over Pa0 as AA, or this is called thermodynamic activity of A, right. So, in terms of thermodynamic activity we can state Rawls law as AA is equal to Xa, right. So, this is the Rawls law, and we can define this parameter Re prime A by Rea we can replace by parameter gamma A, right, where gamma A is called the thermodynamic activity coefficient. Right. So, when we have dilute concentration, we know there is a linear relation between A and Xa, and so gamma A is constant at dilute concentration, or this is the Henry's law. Okay. So, this gives us the physical significance of the term thermodynamic activity. What is it? So, basically activity is a ratio of equilibrium partial vapor pressure of A exerted by the solution to the equilibrium vapor pressure exerted by pure A at the given temperature T, right. And we know if gamma A is less than 1, right, that means AA is less than Xa, and this occurs when Re prime A is less than Rea, right. So, the intrinsic rate of evaporation in solution is less than intrinsic rate of evaporation in pure A, which means the intrinsic evaporation tendency of A is reduced when it goes from pure state to the solution, right. So, what is evaporation? The atom is trying to escape from the solid, right. So, basically that defines the escaping tendency of the component, in this case A, right. If activity AA is less than XA, that denotes negative deviation, which means the intrinsic escaping tendency of A is reduced by going into the solution. On the other hand, if we have AA greater than XA, right, in that case the intrinsic escaping tendency of A increases by going into the solution. We are comparing the intrinsic escaping tendency in solution with that in the pure state, right. So, basically here this pure state we are taking as a reference state, or it is called the standard state. Okay. So, this is the significance of thermodynamic activity. Now, when we are analyzing the intermixing process or the process of mixing, we need to see what are the Gibbs free energy changes associated with it, so that we can decide the equilibrium or stability criteria based upon that, right. So, we will see how the Gibbs free energy changes are calculated for the mixing process. Before that, it is first important to define the contribution from individual element to the total property of the system. For example, Gibbs free energy or volume, basically the extensive property, right. So, the contribution per mole from the individual component to the total property of the system is referred to as partial molar quantity. Partial molar property is denoted by Qi bar, and it is defined as partial of Q prime with respect to number of moles of Ni at constant temperature, pressure and constant number of moles of other components. So, this is basically the change in property Q prime by the addition of 1 mole of I when we keep temperature, pressure and other numbers of moles constant. Again, this has to be done at constant composition, right, because then Qi bar will also change with composition. So, when we add this 1 mole to the system to define Qi bar, it has to be added to a large amount of the system. So, that addition of 1 mole of I does not change the composition significantly. Okay. So, now we know then Q prime is a function of temperature, pressure and number of moles of all the species. So, let us consider n component system, and Q prime basically is a state function. Q is a state function, right. So, it has a exact differential. So, at constant temperature and pressure we can define its differential as dq prime is equal to dou q prime by dou Ni at constant temperature, pressure in J not equal to I dNi plus dou q prime by dou Nj at constant temperature, pressure I not equal to J dNj and so on. And we can see these partials are nothing but the partial molar quantities. So, dq prime is nothing but Qi bar dNi plus Qj bar dNj and so on. Right. So, let us denote this by equation 1. Now, as I said, a partial molar property is basically the contribution per mole of species I to the total property Q prime, right. So, we can mention Q prime as Ni Qi bar plus Nj Qj bar and so on. So, if we take a differential of this, we get Qi bar dni plus Qj bar dnj plus ni dqi bar plus nj dqj bar and so on. Let us denote this by equation 2. And if we compare equation 1 with equation 2, we see that Ni dqi bar plus Nj dqj bar and so on should be equal to 0. Or if we divide this equation by the total number of moles of the system, then we can write xi, where xi is the mole fraction of I, dqi bar plus xj dqj bar and so on equal to 0. Right. So, both these equations are equivalent and they are called Gibbs-Duhem equation. So, these are very important equations. The Gibbs-Duhem equation will be very important for our class. We will keep using it as we go along. But what is the physical significance of this? It essentially tells me that not all partial molar quantities are independent, right. Practically, why it is important? Because many times we find that it is possible to, if for example, if we are considering a binary system, it is possible to measure the property of only one component. Measuring property of second component is not practical, many times it happens, right. But this equation tells me that is okay. If I can measure the property of one component as a function of composition, then from the Gibbs-Duhem equation I can get to the other property. So, that is the physical significance of this Gibbs-Duhem equation. Okay. And this is very important. For example, we will often talk about molar volumes when we study the diffusion, because the analysis of diffusion profiles is considerably affected by the changes in molar volumes, right. So, the volume is one extensive property. So, obviously, we have a partial molar volume, which is the contribution per mole by individual species to the total volume of the system. So, in terms of mole fractions, we can write molar volume as xi Vi bar plus xj Vj bar and so on, where Vi bar Vj bar are the partial molar volumes. Right. And we can write the Gibbs-Duhem equation as, we can write in terms of summation xi dVi bar equal to 0. Similarly, if we consider Gibbs free energy, molar Gibbs free energy, we can write G as xi gi bar plus xj gj bar and so on, where by the definition of partial molar quantities, gi bar is defined as dou g prime by dou ni at constant temperature, pressure and constant number of moles of other species. This looks familiar. So, this is equivalent to the chemical potential, right. So, the partial molar Gibbs free energy of I in a solution is same as its chemical potential mu I in the solution, right. So, we can write the Gibbs-Duhem equation for chemical potentials as xi d mu I equal to 0, right. So, these two equations are very important. We will use them in the later part of the class. Okay. So, now how do we analyze the Gibbs free energy changes associated with the mixing process, right. So, if we mix A and B to form a solution, what is the Gibbs free energy change associated with it, right. So, let us carry out that mixing process systematically. Suppose initially we take x A moles of A and x B moles of B, right, and we form 1 mole of solution, right. So, what will be the initial Gibbs free energy of the system? Let us call it G1, x A G A 0 plus x B G B 0, where G A 0 and G B 0 are the molar Gibbs free energies of A and B, right. What will be the Gibbs free energy after formation of solution? So, let us call this G solution, right. In terms of partial molar Gibbs free energy, it will be x A G A bar plus x B G B bar, right. So, the Gibbs free energy associated with the mixing process, more specifically this is molar Gibbs free energy, because we are forming 1 mole of solution from x A moles of A and x B moles of B, that will be delta G mix G solution, the final Gibbs free energy minus initial Gibbs free energy, and if from these two equations we can write it as x A times G A bar minus G A 0 plus x B times G B bar minus G B 0. What is this quantity? G A bar minus G A 0. So, it is basically the change in Gibbs free energy associated with A when it goes from pure state into the solution. So, this is we can call as delta G M A bar or partial molar Gibbs free energy of mixing of A, right. So, we can write delta G mix as x A delta G M A bar plus x B delta G M B bar. Now, we need to evaluate delta G M A bar and delta G M B bar. So, let us see what happens to the individual species form a solution from the pure state, right. So, what we are doing, if we consider A, we are taking x A moles of A from pure A, right, and putting it into a solution, right. Now, when I had pure A, the partial pressure exerted by A was P A 0. When I have A in solution, partial pressure exerted by A is P A. So, essentially we are changing the vapor pressure of A from P A 0 to P A, right. So, this solution process can be considered as is composed of essentially 3 steps, right. So, consider the first step is consider evaporation of 1 mole of A at temperature T. So, suppose pure A is at equilibrium, we evaporate 1 mole of A at constant temperature pressure from solid state to the vapor state. Then reduce the pressure of A from P A 0 to P A, and then third step as condense the 1 mole of A into the solution, right, at P A and temperature T. So, this step 1 and 3 are essentially the reversible processes, right. Evaporation of 1 mole of A at T and PA0 is reversible. Similarly, step 3 is reversible, but step 2 is an irreversible process. So, there will be the Gibbs free energy change associated with step 2, right. Now, this we can replace with a reversible process and find out what is the Gibbs free energy change associated with it. So, essentially we are trying to see what is dG. We know it should be equal to minus S dt plus V dP, and at constant temperature you know dG is equal to V dP. Now, if we consider ideal gas, we are considering vapors, right, and the vapor pressures are typically really low pressures, right, and we know at low pressure we can consider a gas, a real gas, as close to an ideal gas, right. So, we can apply the ideal gas equation here. So, we can replace V with RT by P. So, if we make a state change from pressure 1 to pressure 2, we know delta G should be equal to RT at constant temperature, delta G should be equal to RT ln P2 by P1, right. So, in this case when we carry out these 3 steps, that delta G is equivalent to delta G A bar m, right, and we are changing the pressure from PA0 to PA. So, delta Gm A bar is RT ln PA over PA0, and PA over PA0 is nothing but thermodynamic activity of A. So, this is equivalent to RT ln AA, right. So, the Gibbs free energy of mixing you know should be equal to X A RT ln AA plus X B RT ln AB. In general, for an n component system, we can write the molar Gibbs free energy of mixing should be equal to sigma I for n components should be equal to RT is constant Xi ln AI, or delta Gm I bar is equal to RT ln AI. Now, we know delta Gm I bar was Gi bar minus Gi 0. So, this we can also write as Gi bar is equal to Gi 0 plus RT ln AI. Again, this equation you all are familiar with, I suppose, because Gi bar is nothing but mu I. So, we can write this as mu I equal to mu I 0 plus RT ln AI. Okay. So, now we know the Gibbs free energy change associated with mixing process, or when we form a solution from pure components, what should be delta G mix. And this is the standard equation for chemical potentials that we will be using, mu I equal to mu I 0 plus RT ln AI. So, in this case mu I 0 is nothing but the chemical potential of I in its standard state, right. You can define any state as standard state. In this case our standard state was pure I. More specifically, the standard state conventionally is defined as pure component I in its stable state at the temperature being considered. Okay. So, essentially the solution thermodynamics boils down to the study of temperature, composition, vapor pressure interrelationship, right. Because we studied when we form the solution how the pressure of vapor above the surface of the solid or liquid, the condensed phase basically changes, right, and this vapor pressure will of course be a function of temperature, and the vapor pressure intrinsic rate of evaporation also changes with composition. So, the solution thermodynamics essentially deals with interrelationship between temperature, composition and vapor pressure. Okay.